Hello everyone, welcome to Sai Tutorials Jamkandi. Here 8th, 9th, 10th class Kannada medium and English medium math, science, English classes are available in the regular classes as well as in the online classes. So please join us and start learning. So dear students, in this session, in the previous session I have discussed some concepts related to the second chapter, that is physics. The next concept relating to the second chapter, that is electric potential and capacitance for second PUC physics. In the previous session, you can watch electrostatic potential, the introduction part of the electrostatic potential and what are the important criteria are discussed here. And the mathematical expression and the potential energy per unit positive charge at a point in electric field and potential charge potential due to a point charge and potential due to a charged spherical conductor both inside and on the surface and also the outside the surface of the conductor. Now, so this much is over, right? What is the definition is over? Electric potential, the mathematical expression of electric potential at a point at a charge q and at a distance r is over. So what is the potential energy? Electrostatic potential at a point v due to that change in potential energy. And what do you mean by the potential energy per unit positive charge at a point in an electric field? So it is also called as electric potential at a point. And by considering this figure, I have discussed in the previous session that potential due to a charged spherical conductor and for a point on the surface or inside the conductor of the potential. And now let us discuss about the work done. Okay, the work done in moving a charged particle from one point to another point in an electrostatic field. So, okay, in this today's session, the very important concept related to the second chapter, that is the work done in moving a charged particle from one point to another point in an electrostatic field depends only on initial and final points. See, I have discussed the work done. Okay, I have discussed work done where it is denoted by the letter W. Okay, see the work done in moving a charged particle, it is having some a kind of property or a kind of criteria. What is the criteria means? The work done, okay, the work done in moving a charged particle from one point to another point in an electrostatic field depends only on the initial, okay, only on the initial and final points, but not on the path between the 2 points. This is a very important to be noted. Say, suppose if I consider the 2 points, that is A and B, okay. Observe carefully. Let us consider the 2 points, that is A and B in an electrostatic field. See the work done. Okay, the work done in moving a charged particle from one point to another point. See, to move the charge from one point to another point, there will be some work is done. Okay, there will be some work is done. So that work done in moving a charged particle from point A to point B in an electrostatic field depends only on the initial. Okay, so suppose the charge q1, it is moving from point A to B. Okay, it depends only on the initial point. What is the initial point? Point A. Okay, point A, and the another point is B, but not, okay, but not the path between the 2 points. So whatever it is moving, no, whatever it is moving, like first thing is from point A to B, it is moving like this is the one, okay. And if a path, suppose it will go or it will move like this in a zigzag manner, it will move like this. And suppose if it, in a third manner, it will move like this, or it can be like this, okay. Suppose the path between, okay, the path between the 2 points, it will not be considered, but only that point charge, the movement of that point charge from point A to B is considered, not the path. So in figure, the work done per unit charge in moving from point A to point B along all the paths, suppose let us consider the 1 2 3 4 are equal. Suppose if you consider the work done, that work done in moving up from point A to B along all the paths will be 1, 2, 3, 4 are equal. Then W1, okay, then W1 is equal to, if those are equal, then W1 is equal to, W2 is equal to, W3 is equal to, W4 is equal to, or we can also say it as a total work done. Okay, now the work done is equal to the potential difference between the point A to point B. So, work done in moving a charge over a closed path in an electric field must be 0. Why it will be 0? So, whatever the charges are moving inside, okay, inside the conductor, I mean inside the closed path, the electric field will be 0. So, electric field is a conservative field. Why? Because electric field is a conservative field. So, the work done in moving a charge particle from one point to the another point to in an electrostatic field depends only on the initial point and final points, but not the path between the 2 points. Suppose if you consider work done per unit charge in moving from point A to B in many directions, okay, many paths. So those are equal, then this will be the criteria. So now the work done will be the VA minus VA difference VB. So work done and other property, that is work done in moving a charge over a closed path in an electric field will be 0. So it is a conservative field. It is a conservative field. I hope this concept is clear to you. Now, the electric potential. Okay, the electric potential at a point due to a positive charge is positive and due to negative charge is negative. So, the net potential at a point is a algebraic sum of the potential due to the different charges. Okay, electric potential is a scalar additive. These are all the sum of the important properties. See, if I consider any closed surface area, any conductor, or suppose if you consider any conductor or any medium, there will be a number of charges, whether it may be positive or negative charges are present over there. Then the electric potential at a point due to positive charges is positive and negative charges is negative. So the net potential at a point is the algebraic sum of the potential due to a different charges. So it can be written as potential. Electric potential will be, suppose it may be plus Q, suppose it may be minus Q, minus V. I mean, due to a point charge 1, point charge 2 and point charge 3. Whether it may be positive or whether it may be negative. So, the electric potential at a point due to positive charges is positive and negative charges is negative. So the net potential at a point in that conductor or in that medium will be the algebraic sum of the points due to different charges. The electric potential is a scalar additive. Those algebraic sum will be the scalar, not the vector. It is a scalar additive. Only the potential difference between the 2 points. That is, VA minus VB has a definite value. But absolute values of VA and VB are arbitrary and they have no physical significance. They are arbitrary. I mean they are. Suppose if I consider the point charge at a having Q, the potential. Okay, the potential will be related to that point charge only. It is only arbitrary, not any. It is having no physical significance, but it is a permanent, or it is having no any physical significance. It is constant, or it is arbitrary in nature. Okay, only potential difference between the 2 points is a physically meaningful. When it will be physically meaningful, only when it will be the potential difference. Okay, when it will be the potential difference, then only it is having the physical meaning. Suppose VA difference VB, then only it has having some physical significance. Okay, this is another property. Say the potential difference between the 2 points. Okay, suppose the potential difference between the 2 points is a work done in moving 1 coulomb of positive charge from point to the other. It is measured in volt. I have said you. See, the potential between the 2 points is the work done in moving 1 coulomb of positive charge. See, suppose if you consider the charge Q, it is having 1 coulomb. Okay, it is having 1 coulomb of positive charge from one point to the other. It is measured in volt. Electric potential at a point due to a short dipole is given by. So we need to derive this expression. So let us derive this, where P is an electric dipole moment. So let us derive this expression now. Say the potential difference between the 2 points. The potential difference between the 2 points is the work done in moving 1 coulomb of positive charge from one point to the other. It is measured in volts. Now, see, the work done in moving a charged particle from one point to another point in an electrostatic field depends only on the initial and final points. This is one property. Work done in moving a charge over a closed path in an electric field is zero. This is another property, because this is a conservative field, and electric potential at a point due to a positive charge is positive and due to a negative charge is negative. The net potential at a point is the algebraic sum of the potential due to different charges. No, it is a scalar additive. The whatever the sum of algebraic sum is there, no, it is a electric potential is a scalar additive. That must be scalar. Okay, only the potential difference between the two, Va minus Vb, has a definite value, but the absolute value of Va and V are arbitrary. It has no any physical significance. When it will be physically meaningful, because of the when it will be physically meaningful, when it will the potential difference between the 2 points is considered, then it is a physically meaningful. When it will be considered as a physically meaningful only when the potential difference between the 2 points is physically meaningful. So the potential difference between the 2 points is a work done in moving 1 coulomb of positive charge from one point to the other. It is measured in volt. Now let us consider the electric dipole. Okay, electric potential at a point due to a short dipole is given by this thing. Let us derive this expression. Point due to a short dipole. Okay, just a second. Electric potential please note it due to dipole. Okay, electric potential due to a dipole. How it will be derived? Let's see. Let us consider an electric dipole. Okay, let us consider an electric dipole consisting of two equal charges, that is Q equal and opposite charges separated by very small distance. See, let us consider the dipole, electric dipole. Let's see. Okay. Let us consider the electric dipole here. This is having the point A. and this is having point B. Okay. Which is separated by a small distance, that is 2a. Electric dipole, that is 2a from the point of origin O. If q is a charge and 2a is the length of the dipole, then electric dipole moment will be, what will be the electric dipole? That is P is equal to 2a into q. Am I right? 2a into q. Now 2a into q. Let AB be a dipole whose center is O and P be the point at a distance r from the center of the dipole. I have considered this is a point, dipole. Now let us consider a point P here. Okay, let us consider a point. It is having the point A and it is having the point B. Okay. Now let P be a point at a distance r. This is the at a point P. It is having some kind of distance r. And this is having the distance to A. This is the point O at the point origin. Now at an angle theta by OP. This is O. This is have an angle theta. Okay, this is having an angle theta. Let BN and AM be the perpendicular lines drawn on OP. Okay, let BN and AM be the perpendicular line. Suppose if I consider at point, this is N. This is N point BN. And suppose if I consider AM, this is a M. This is M. Okay. It is having some kind of distance to R. Am I right or not? To R. See, now electric field due to a plus Q charge. This is plus Q and this is minus Q charge. Okay. Now electric potential due to a positive charge, that is V1. Okay, let us write V1 is equal to, what is the potential formula? Electric potential formula is 1 by 4 pi epsilon naught into, due to a positive charge, that is Q divided by R1. Okay, R or R1. This is distance R1. Okay, now electric potential due to a negative charge. Sorry, this is positive charge and this is, let us consider this is positive charge, or you may consider that also. And this is negative charge. Okay. So the electric potential due to a negative charge V2 is equal to 1 divided by 4 pi epsilon naught is equal to into minus q divided by R2. This is R2. Okay, R2. Now the total electric potential. What will be the total electric potential then? Suppose, keep it the mind, total electric potential due to a point charge. Total electric potential due to a point charge will be, see, that is V. Just a second. Okay, V is equal to V1 plus V2. Am I right or not? Now V will become, what will V become? 1 divided by 4 pi epsilon naught into positive charge Q divided by R1 plus 1 divided by 4 pi epsilon naught into minus Q divided by R2. What will be the common here? V is equal to 1 divided by 4 pi epsilon naught is common and Q is also common. So suppose if you take common, 1 divided by 4 pi epsilon naught and Q is also common. What will be the inner difference? That is 1 by R1 minus 1 by, sorry, minus 1 divided by R2. where R2 is BP. Okay, sorry, R1. So in the previous page, R1 is PB. Am I right? And NP. Okay, and NP is also equal to, okay, if R1 BP is R1, then MP is also R1, because the total difference between A to P is 2R. So if you divide those two, then it will be the R only. It will be the only R. This the whole difference is R2 2R, right? So the half of this is R1. Next, so R1 is equal to, okay, R1 is equal to BP, whose difference is also equal to NP. So OP minus NP can be written as OP minus ON. Look at the diagram while I'm saying. So in triangle, suppose if you consider triangle NOB, okay, this is this is NOB. Suppose if you consider the triangle NOB, then ON divided by cos theta will be ON divided by OB. Cos theta will be ON divided by OB. So cos theta, suppose if you consider the triangle NOB, cos theta is equal to ON divided by OB. Am I right or not? Then ON is equal to, so what is the OB? Half of the difference between 2A, that is, so A into OB is A into cos theta. A into cos theta. Now R2 is equal to R2. Okay. Just a second. R2 becomes, R2 is equal to OP minus, if you consider the diagram, OP minus ON. So what is OP? Look at the diagram. What is OP? R. And what is ON we have derived? A into cos theta. Okay. Now in triangle, suppose if you consider the triangle MOA, then cos theta will become OM divided by OA. Cos theta will become OM divided by OA. And consider triangle MOA. Then cos theta will become OM divided by OA. Okay. So what is OM and OA? Let us discuss. OM will become, okay, OM will become A into cos theta. A into cos theta. So R2 will become OM plus OP plus OM. That is OP plus OM. So what is OP? R plus cos theta. So we got the values R1 and R2. Suppose if you substitute in the total potential, electric potential, that is in the equation, this thing. Okay, suppose if you substitute those values in the equation, we will get V is equal to Q divided by epsilon naught. We took common Q divided by epsilon naught. So this is Q, not A. And if you substitute in this equation, that is R plus A cos theta whole divided by and minus R minus A cos theta whole divided by R square minus A square cos square theta. Okay. So this this R and this R get cancelled. Now what will be the potential then? V is equal to Q divided by 4 pi epsilon naught into A cos theta plus A cos theta will be 2A cos theta divided by R square minus R square into cos square theta. Okay. R square minus, sorry, this is A square actually, not R square. A square cos square theta. See here, 2A into, I have told you that P is equal to, what is the dipole? 2A into Q. 2A into Q. So that's why V becomes P into cos theta whole divided by 4 pi epsilon naught into R square minus A square, just a second, R square minus A square cos square theta. Am I right or not? This is the actual expression. This is the actual expression for electric potential due to a dipole. Okay. So for a short dipole, if you consider for a short dipole, here R is greater than 2A, or sorry, A only. For a short dipole, R is greater than A only. In that condition, we will become 1 divided by 4 pi epsilon naught into P into cos theta. P into cos theta divided by r square. Okay. This is the expression for electric potential due to a dipole. So this is the electric potential due to a dipole. So if you remove the cos theta, in the vector formation, it will be written as P bar dot R bar R cap divided by 4 pi epsilon naught into R square. This is the expression for electric potential at a point due to a short dipole. I hope this derivation is clear to you. In that case, some important note to be written. See, potential at a point due to a dipole on the axial line. So on that condition, so I have considered the expression for electric dipole on the axial line. If a point P on the axial line, that theta is equal to 0 degree, the theta will become 0 degree. If it is axial, then cos theta will be 0 degree and is inversely proportional to the way that, and that at that point the dipole moment, that dipole will become is inversely proportional to the square of the distance from a dipole, that is at a large distances. It will become V is directly proportional to R square. V is inversely proportional to R square, whereas for a point charge V is directly proportional to 1 by R. Now the potential is maximum, that is theta is equal to 0 degree or pi, then cos theta will become plus or minus 1 along the axis of the dipole. Along the axis of the dipole. Now if at a point, if any point on the equatorial line, at that condition the potential will become 0. So what will be the cos 90 degree? It will be 0. So thus the equatorial line of a dipole will become 0. Then the equipotential due to a system of charges V is equal to 1 by 4 pi epsilon naught into Qi divided by Ri. Okay. I have told you in the first chapter, for a continuous charge distribution, V is equal to line integral of dq divided by 4 pi epsilon naught into r, because we in the continuous charge distribution we need to consider if I consider the charge distribution in a conductor, I need to consider the small surface or the small area for the consideration. Then here dq becomes lambda into dl, where lambda is a linear charge density. Okay, linear charge density. And for surface integral, it is dq is equal to sigma into ds for a surface distribution of charges, for linear charge distribution and for surface charge distribution. And dq is equal to rho into dv for volume distribution of charges. In the first class, that is for electric charges and fields, I have discussed you the whole concept related to this a continuous charge distribution. Okay, so in the same way, the potential, electric potential due to some point charges, if you consider the linear charge distribution of charges, or suppose if you consider for a surface distribution of charges and for a volume distribution of charges, where lambda, sigma and rho are the densities, that is linear charge density, surface charge density and volume charge density. If you go on putting these values in this equation, you will get the continuous charge distribution. Continuous charge distribution. So this is all the concept we have discussed in today's session. So let me revise. Okay, in 2 minutes, within 2 minutes I am going to revise whatever I told you in this session. So in the first and foremost concept I have told you today is the work done in moving a charged particle from point 1 to point 2 in an electric field depends only on the initial and final points, but not the path. Suppose if you consider the work done in moving the point charge from A to point B in any path, those are going to be equal. Okay, the work done will be difference between the potential. So suppose that the work done in moving a charge over a closed path in an electric field will be 0. So because It is a electric field is a conservative field. So the electric potential at a point due to positive charges is positive and negative charges is negative. The net potential at a point is an algebraic sum of the potential. Whatever the sum is there, no, it is a scalar additive, and only the potential difference between the 2 points has a definite value. So here VA and VB are arbitrary. It is having no physical significance, but only it will become meaningful, physically meaningful. And when it will be physically meaningful, when it will be considered as a potential difference. When the difference between those 2 points will be taken, then only that is physically meaningful. Now the potential difference between the 2 points is the work done in moving 1 coulomb of positive charge from one point to the other. It is measured in volt. Points to be remembered. Now I have derived the expression, and in this session electric potential at a point. It is very important concept. You need to note down. It is very important concept. Okay, electric potential at a point due to a short dipole. It is given by V is equal to Q into 2A into cos theta divided by 4 pi epsilon naught into R square, or where your Q into 2A is P bar into, in the vector notation, P bar into R cap divided by 4 pi epsilon naught into R square. So where P is a electric dipole moment. So it is having some cases where if you consider the potential at a point due to a dipole on the axial line, is when it will be axial line is inversely proportional to square of the distance. Whereas for a point charge, V is inversely proportional to R. So potential is maximum. When it will be maximum? Suppose if you consider theta as a axial line, on the axial line, that is theta becomes 0 degree or pi degree, then the value of cos theta will become plus or minus 1 along the axis of the dipole. So suppose if at any point on the equatorial, that is perpendicular to the potential, will be 0. Okay, the equatorial line, the potential will become 0. The electric potential due to a system of charges will be given by like this. And if you consider the continuous charge distribution of charge, then the equation will be V is equal to the line integral of dq divided by 4 pi epsilon naught into R. So for a linear distribution of charges, for surface distribution of charges, and for volume distribution of charges, where lambda, sigma and rho are the linear charge density, sigma is the surface charge density, and rho is a volume charge density. So this is all about the concept related to your syllabus. So I hope this session is helpful to you. So please, whatever the concept I have told you in this session, please practice twice or thrice up to you get the knowledge about this concept. So don't try to forget this. And also don't forget to subscribe our channel. Please support and learn more. So I hope this concept is clear to you in this session. So dear students, let us discuss the next concepts in the next session. So by this, I'm going to wind up the session. Thank you.